All right, folks, let's go ahead and get started. So just a reminder, your third exam should go live as soon as I finish it. I'm aiming for 6 o'clock. I'm a little concerned I'm not going to make that self-imposed deadline because it's taking me longer to get things up and running in Canvas than I anticipated. But it'll be happening sometime tonight either way, and you'll have 48 hours from the time that I post it. More than likely, it'll be due a little bit after 48 hours. So, sometime Wednesday at midnight is more likely what's going to happen. But that's when it'll be due. I will remind you that the exam is going to have two parts. There's going to be the part where you type in your answers. It's going to look a whole lot like your homeworks do. But in addition to that, there will be a separate add-on assignment. And what you'll do there is you'll upload your work. That way I'll be able to give you partial credit so that unlike the homeworks where if you get a question wrong, that's the end of the story. Here I can look at your wrong answer and then go back and look at your work and assign you additional points based on how close your work was or what kind of mistakes you made. So it'll be very much like the way I would normally grade an exam. It's just going to happen in two parts. The exam, once you open it, it's going to give you 2 hours. So make sure you have 2 uninterrupted hours in which to do the exam. You won't be able to save it and walk away. So it is timed. It's a strict time limit. The upload of your work needs to happen promptly after you finish the exam. I don't have a hard limit on that, but if it's taking more than about 15 minutes to get that thing uploaded, I'm going to start looking at you funny. So please, unless there's some sort of weird technical reason, you should be able to get that up pretty quickly. Make sure that anything you upload is something that I can read. It's got to be legible. And it's also important that you clearly mark where your final answer is on your work, because that final answer on your work needs to match what you signed up or what you put in on your original answer. If you fail to do that, I may not award partial credit if you fail to follow those instructions. But that'll happen sometime later today. In the meantime, we had been talking about wave optics, and the next thing we need to sort of tackle, and we're going to talk about that briefly, then I'm going to let you guys go, is what they call thin film interference. It's going to happen because you've got waves of light that interfere with one another, and you've probably seen this effect before. If you ever gotten out of your car in a parking lot in the rain and there's puddles there, and because it's like in a parking lot, there tends to be like a layer of oil that floats on the top of those puddles. And what ends up happening is you see these kind of weird sort of rainbow patterns that sort of move and shift on top of that. You may have also seen this effect if you've ever looked at, say, a soap bubble floating through the air. You'll see sort of weird rainbow striations, little stripes of various colors on that surface. We're going to talk about what that effect is and how that effect comes into play. And it all has to do with thin films. So for this, let's start with the assumption that I've got two materials, one on top of the other. So imagine here's like my puddle of water in the parking lot. So down here, I've got water. And then what's going to happen is because oil doesn't like to mix with water, you'll get this layer of oil that's very, very thin floating on the top of the water. And then, of course, above the oil, you've got air. Now, what's going to happen is when you have light that is incident on the air, some of that light is going to hit this layer of oil on the top, and it will reflect. And of course, you might be seeing that little ray of light. But some of the light that is impacting on the oil is not going to reflect off that top surface. It instead is going to penetrate the oil, refracting in the process, And you'll notice that it's going to get bent a slight little amount. And then when this ray of light hits the interface between the oil and the water, it again has the choice of either reflecting or refracting again when it enters the water. So if you're up here and you're looking at the light coming off of that puddle of water, bouncing off of that thin film, what you're going to end up seeing are some light that bounces off the top layer where the surface of the oil is, and another ray of light that bounces off of the bottom layer between the oil and the water. And these two rays of light, they're both waves. And as waves, they can tend to interfere with one another. And we saw this same sort of interference thing when we were doing the double slit experiment the other day. There's a condition under which I'll either get constructive interference between these two waves or destructive interference between those two waves. And it's all going to have to do with the path difference between how far the first wave has traveled and how far the second wave has traveled. You'll notice if both of these rays of light are incident on your eye at the same time, then what's going to happen is this top wave has traveled this distance, but this second wave has traveled a little bit of extra distance down here. It's gone into the oil, then back out of the oil again. And so the difference in path length is the length of this part of the path right there. I'm going to call that length delta L, much like we did last time. So delta L is just how much further the light that has gone into the oil and bounced off of the water underneath it has gone compared to how far the light that has bounced off the top surface has gone. And we're going to make some simplifying assumptions that are going to make our lives a little bit easier, right? You'll notice that like this path that it travels, it's going to be kind of like a weird triangular path. And what's going to happen is the actual like super detail oriented distance that it's going to cover, in order for me to figure that out, I'd have to know things like what the thickness of the oil is. I'd have to know the angles that these make. It would be a trig problem. And we could do it, but it would be kind of complicated. It would depend on like what the indices of refraction are and how much this light bent. And that would be a tough problem if we tried to solve it. We could do it, but we don't necessarily want to. However, in this particular example, we're talking about a thickness that is very thin. This layer of oil is incredibly thin. It's only a few molecules thick generally. And what that means is that for the most part, this kind of diagonal distance right here is not going to be all that different from the straight up and down distance here. And even this diagonal distance is not going to be all that much different from this, provided that this thickness is super thin. Now, the thicker you make that layer of oil, the less likely this particular approximation we're going to make is going to pay off. But we're going to assume that this distance is very tiny. And if that distance is very tiny, we can get away with approximating and saying that basically this distance is going to be d on the way down and then another d on the way back out again. So we can call delta L approximately 2d. Does that make sense? Again, d is the thickness of our very thin film of stuff. So, I'm sorry, I didn't catch that.
Because it refracted one time and then reflected a second time.
Right. The idea is it's refracting here and it's going some angle across this way, and then it's reflecting down here and going some angle here. And if we knew those angles, we could do the trig much more precisely. But by assuming that d is very tiny, we're going to approximate it as being roughly about 2d. Now, in actuality, it's going to be a little bit longer than 2d, but we're going to get away with kind of imagining that it's not. Does that make sense?
Yes.
Okay. So Now the question is, if we know how big that path difference is, I want to know how is that going to relate to how these two beams of light end up interfering with one another. And again, I'll harken back to our previous discussion where we solved the problem with the two lenses. And what we found is that if I had two waves that started out in phase, but one of them has to travel further than the other, what's going to happen is in order for the peak of one wave to arrive at the same time as a peak of the other wave, the difference in path has to be related to the size of the wavelength of my light. If this distance, delta L, is going to end up equaling the wavelength of my light times some integer, then what will generally happen is, if that's the case, I'm going to end up with the peak of one wave arriving at the same time as the peak of another wave. Even if it's like not the ones that left at the same time, it might be the one who arrives first arriving at the same time as the guy who left on the other side a little bit earlier. In other words, if I've got a wave at the top that looks like this, and a wave from the bottom that looks like this, what's going to happen is the wave from the top doesn't have to travel so far. So this guy here will not arrive at your eye at the same time as this guy here. But what might happen is this guy here might arrive at the same time as this guy or this guy, somebody further back in the line. And again, we saw that same sort of behavior last time. So if that's the case, you would normally expect to get constructive interference. However, if we're different by not one wavelength, but an integer plus a half wavelengths, we would expect this to be a situation in which the peak of one wave will arrive at the same time as the trough of the other wave, and they will always tend to cancel out. That's destructive interference. So normally, these would be my two conditions. However, there is a slight hiccup in this simplified understanding. And to see that hiccup, let's go back to my trusty rusty bending light simulation and see if we can't spot something that might be an issue when I'm making this approximation. So where's my bending light guy? Oh, he's right there. So what's going to happen? I'm going to shine my little laser light from one medium to the other. And I'm going to turn on the wave picture because it's going to make obvious something that's going to be important. What can you tell me about the wavelength of this laser beam in this simulation right now?
Do you want to know anything about this wavelength?
Tell me something that you can observe about the wavelength of that wave right now.
The index of refraction is 1.5.
That's true, but that's not about that. You're not telling me about the wavelength.
Oh, okay.
You're telling me about the index of refraction. Look at that picture and tell me what that picture tells you about the wavelength of that light.
Did it get smaller?
Aha! That's true. Because look, you can literally see it. Up here, when my light is traveling through the air, you can see the distance between those two wavefronts is relatively large, right? It's starting off at 650 nanometers, right? That's what it says over here. But that's the wavelength that it has when it comes out my laser. Now, what's going to happen, though, is that when the light leaves the air and enters my layer of oil, it slows down. And when it slows down, the frequency stays the same, which means the wavelength has to get smaller. Hey, whoever's got your mic unmuted, please. Thank you. So what's going to happen is this wavelength inside the oil is not the same wavelength I have out in the air. And that's a problem because in our example, what's going to matter is if that path length difference is going to end up being different by a certain number of wavelengths using the wavelength that it has in the oil, not the wavelength that it has in the air. And that makes things a little trickier for us. So what we're going to have to do is make an adjustment to that formula that I was showing you to take into account that the wavelength changes when it enters the oil. So, darn it. There we go. So if this is the wavelength that my laser had originally, that's not the wavelength I want to use in this calculation. And what's going to happen is the wavelength I have inside the oil, I'll call this the wavelength in the oil, is going to be my original wavelength divided by whatever the N of the oil is. So what I'm going to do is I'm going to take this lambda that I have, and I'm just going to go ahead and divide it by N in both places, where this is the index of refraction of the thing that it's traveling through. And this is the wavelength that it had originally, not the wavelength that it has inside the oil. If I don't make that adjustment, I'll get a slightly wrong answer. So that's complication number one. There's a second complication. And that second complication comes from the fact that sometimes when waves reflect, they behave in a way that upsets this model. And I can sort of show it to you. Again, I'm going to go back to my trusty set of simulations, but this time I'm going to look at a different simulation. I'm going to look at the one we used last semester when we first started talking about waves on strings. And there was a behavior that we may have made note of last semester, but I don't think I called too much attention to it. And it has to do with what happens when a wave reflects. So let's go back to screen share.
What's the question again, Dr. Fleming?
Yes, sir.
No, I was asking, what was the question that you asked?
Well, I haven't asked a question yet. What I've suggested is that we've seen a behavior when waves reflect before that's going to change our answer here. I have to add some nuance to this thing we're doing based on something we're about to see.
I see.
So hold that thought. So here I've got a wave on a string, and I could have this thing travel with no end. Let's take the damping off so I don't have any friction. And let's have this thing oscillate. And what's going to happen is I'm generating waves over here on the left, and those waves are traveling away from where they start with no end whatsoever. But if I put an end to this other string, if I have a fixed end on the right-hand side of the string, then what will happen is as the wave travels in from the left and it hits the right end of the string, that wave will reflect and bounce back the way it came from. You can see this most easily if I, instead of doing a repeating wave, do like a pulse. So here's a little wave pulse traveling away. And if I fix the end of the string and I send that pulse, watch what happens when the pulse hits the end of the string. It reflects. It bounces back and travels in the opposite direction. So this is the mechanical analog to what happens when a ray of light reflects off of a mirror, right? It's a wave and it reflects. But you'll notice in this case, I have my little wave reflecting off of the end of the string, but every time it does and it changes which direction the wave is traveling, either left or right, it also changes something else. it changes the direction of the amplitude of the wave. When my wave here is traveling to the right, you can see that it's got an amplitude that's upward. But when it reverses direction and it travels back to the left, it ends up with an amplitude in the negative direction. And it's changing its amplitude every time it reflects. But it doesn't have to be that way. Watch what happens if I make this right-hand side, instead of having that end of the string be fixed, I end up having that end of the string be loose. Well, now you can see that what's happening is when it reflects off of the left side of the string where it's still fixed, it's still reversing direction for its amplitude each time. But when it reflects off of the right side of the string, each time it does so, the reflection does not change amplitude. So we call this a shift in phase. We say that when it's bouncing off of the right-hand side of the string here, where the end is loose, it experiences no phase shift. But the left-hand side, where the end is fixed, it's experiencing a phase shift of 180 degrees, or pi radians. And here's why that matters for this problem. It turns out that when light reflects off of a surface, it might reflect in the manner that we see here on the right-hand side of my string, or it might reflect in a manner like it does on the left-hand side of the string. And it is going to depend on what the indices of refraction are of the two materials from which it is bouncing. Sometimes it will shift phase 180 degrees, and other times it will not shift phase. And that is going to be the telling thing. That's going to be the thing that's going to affect what conditions we get interference from. Because if these two rays of light both reflect and neither one of them shifts phase, then this condition will give me constructive interference and the light will be bright, but this condition will give me destructive interference and the light will be effectively negated. However, if one of these rays shifts phase, but the other does not, then what's going to happen is my two conditions are going to flip. The condition that used to give me constructive interference is now all of a sudden going to give me destructive interference. And the condition that used to give me destructive interference will now give me constructive interference. So having no phase shifts means this is true. Having one phase shift means these two conditions are reversed. And what if both of them shift in phase? If both of them shift in phase, we're back to where we started. So it's going to matter which of those two interfaces, if either, experiences a phase shift. Does that make sense?
Yes.
So under which conditions do you have a phase shift? Well, what's going to happen is if you're reflecting off of a medium that has a higher index of refraction from the one in which you are traveling, you will experience a phase shift. So the phase shifts when you're going from a small n to a large n. If you go from a large n to a small n, there is no phase shift. So if that's the case, and I'm looking at this situation where I have air, oil, and water, right? I know the index of refraction of air is 1. The index of refraction of water is about 1.33. Now, What about this oil in between? That's going to depend on what kind of oil I've got. Let's see here. What's the index of refraction?
Can you move your thing up a little bit? Yeah, thank you.
So typical oil, olive oil has a index of refraction of, let's say, 1.46, turpentine about 1.47. Let's go with something like that, something like 1.4 something. So if that's the case, then what's going to happen is this beam that comes in and it bounces off of the surface of the oil, is it going to phase shift or not?
It will.
So this is going to phase shift. But what about this one?
It won't.
Yeah. So what's going to happen is in this example here of light bouncing off of oil and then in terms off of water, then what's going to happen is one phase shift will happen, but the other phase shift will not. And so as a consequence, I'm going to get constructive interference for this condition rather than destructive. And I'd get destructive interference for this condition rather than constructive. It's going to be reversed. Now, why does that matter? Well, what's going to happen is if you've got a thickness of oil that is not very thick at all, maybe only a few atoms thick, that path difference is likely to be on the order of 1 or 2 or so wavelengths of light. And if you are shining a wavelength of light onto that surface that just happens to coincide very nicely with a wavelength for which you get constructive interference, you're going to see that color very, very strongly. However, wavelengths that are a slight bit higher or lower than that are likely to fall into the regime that gets destructive interference. So you shine white light onto that puddle in the parking lot, and what's going to happen is maybe the blue light and the red light, maybe those both can experience destructive interference, and what doesn't get destructive interference is the green light in between. So you're going to see a little green stripe in that region of the puddle. Now, as the oil moves around, the thickness of that oil layer can change ever so slightly. But if you make that oil layer a little bit thicker, now what's going to happen is where you used to see a green stripe, maybe now green light is destructively interfering, but the red light that used to be destructively interfering is now constructively interfering. And suddenly that section of your puddle turns slightly red. And so you've got little regions that have different thicknesses, only different by a super small amount, sometimes just nanometers. And as a consequence, you'll see different colors from each of those areas. Plus, there's also the issue of angles that we've been ignoring. If I have a very oblique angle and my light comes in at some oblique angle, maybe what's going to happen is now that angle makes a little bit difference, and maybe red light refracts at just the right amount to constructively interfere, but the blue light does not. And so that's where you get those weird sort of striping effects or weird color bands. It has to do with this. And what's cool about this, aside from, yay, it's pretty, is you can actually use this effect for making measurements. For instance, if I wanted to know how thick my soap bubble was, I could shine a laser on my soap bubble, and what I could look for is, what wavelengths of laser are going to get me bright stripes and what wavelengths of lasers don't. If I can find a wavelength that gives me constructive interference, I can then, if I know this, and I know the index of refraction of my oil, so I know N, I could solve for how thick that soap bubble was. And they've actually done that in a number of experiments where they're looking at the dynamics of these super thin soap bubbles. You can't measure their thicknesses with a ruler or something because it would pop the bubble. So instead, you shine light on it and you look at the optical properties of the light that comes back. And by knowing this stuff, we can figure out that stuff. Does that make sense?
It does.
Piece of cake. So in terms of that, that's pretty much the end of what we're going to do for wave optics. We could talk about Malice's law and actually, we should probably talk about Malice's law and polarization. And at that point, we're going to be basically done with chapter 27. I'm not going to give you a chapter 27 homework. So the homeworks that are up there now are the homeworks you're going to have. But I don't want to have a homework assignment due during finals week. You're welcome. So we're pretty close to the end of this. So hopefully you're in a good position.
So when is finals week?
Next week.
Next week?
After the classes.
Okay. Do you know when hours will be?
I don't know. There's a schedule for that.
Okay.
Dr. Fleming, we can hear you clearly.
So far.
I can change the date on my mic.
Yeah, now it sounded like staticky off and stuff. So,
All right, can you hear me at all?
yes,
You're
I
coming
can
up
hear you.
really bad.
Is that better?
But,
Better, worse?
better.
Yeah, I switched microphones to see if that makes a difference. So what's going to happen is, normally we would have the exam at a particular time.
Mhm.
What's going to happen because it's online is, sometime before that time next week, I will post the final exam, and it'll be very much like exam 3 is going to be. It'll be available, for the week up until the posted time. It'll be a timed exam, so whenever you start it, you'll have 2 hours. So if you wanted to start it early, you certainly could.
Okay.
But it will be due at the appropriate time so that I have time to grade it.
Right. Okay.
And I think, don't quote me on this, but I think that the 3 o'clock to 4 o'clock time was like Thursday, so it'll probably do that Thursday. I know that graduating seniors have to have their grades in that Friday, and people who are not graduating have to have their grades in by the following Monday, I think.
Okay. Yeah, I need mine in by Friday.
Yeah. So it'll certainly be due, sometime probably that Thursday at the latest, just so I have time to grade them all. But that's where we're going.
Dr. Fleming, so I came in a bit late. Can you talk about the exam 3?
Okay. So exam 3 is going to get posted. I was aiming for 6 o'clock. I may not hit that deadline because it's taking me longer to get my Physics 241 exam coded. One of the issues is that I can't recycle any old questions, and I have to ask different kinds of questions than I normally do for an in-class exam. So I'm having to write them all from scratch. I have to get them all in Canvas, and they have to be clear to the student in a way because I can't clarify them during the exam the same way I would during a proctored exam. So I'm being a little bit cautious about how I ask questions. So anyway, it's taking me a bit. It will be up there sometime tonight, and it will be due 48 hours after that. So it'll probably be due sometime on Wednesday, probably midnight on Wednesday. Once you start the exam, you'll have 2 hours. So make sure you set aside a 2-hour block. Please don't wait until 10 o'clock on Wednesday if the exam is due at midnight, because if you start it then, you have zero margin for error. But that's what we're planning on doing. The number of questions is going to be longer than a normal exam, but only because I'm breaking things up into a lot of smaller parts, and some of the questions are going to be open-ended kind of essay-type questions as opposed to numerical or multiple-choice questions. So it's different kinds of questions than I normally ask.
So are we still having multiple choice?
2 hours enough?
2 hours will be plenty.
Not the way you're talking about the questions, though. Because even like the homework questions does take a lot of time.
Yes, they do. But the homework questions take a lot of time because you don't know what you're doing and you're exploring it as you go. But for an exam, it should take you less time to solve those same questions because you have a better idea of where to start. That's part of the reason that they have a time limit. So.
Okay. And can you also talk about the homework?
Yes, sir. What about the homeworks?
So, a few days ago, you said they will actually go off today. Have you decided?
In light of the fact that the exam's not due for a couple more days, what I've been telling people is that I'll probably make them close not when the exam goes live, but when the exam closes. So you've got a couple more days for doing those.
Would you be
All right,
able
sounds
to
good.
help with 25.4 because
I've had a couple people ask me about that one, so there may be an issue. Let's pull that up and take a look at it. Then,
There's a bug in
You say 25.4?
yeah, yep.
Oh, and can you check, I think it's the instantaneous velocity one too?
That one's not bugged. It's
Okay.
instantaneous. It's not bugged. It is just super sensitive. It's important
Okay.
to use pi in that question. Don't use the pi button. Actually type 3.14 because that's what I used in the.
Oh.
the flaming.
I didn't think about that when it normally doesn't make a difference.
Right.
Which one?
It's here is because you've got a periodic function
Mm-hmm.
has a period that is super tiny.
Right.
If you're off by a tiny amount, that could be multiple periods. So your answer could be all.
Yeah, okay. I'll go with
It's
that.
much more sensitive to round off error than other problems, and that's the thing with that one.
You
So
just have to be really careful with your numbers, basically.
be very careful, and then when you use pi, you actually want to abbreviate it as pi, not or 3.14, not as the pi function. Don't carry it out to extra.
Oh, yeah, that's what I've been doing. Okay.
That'll screw you up.
Okay. Okay. Thank you.
Yeah, that one is just super touchy,
Okay.
but it's not broken. All right, 25.4 you said?
Yeah.
All right, let's see what that one is. All right, let's see here. All right, so for this one here, let's share the screen. Actually, let's share the other screen instead. All right, so here's the question. And what's going to happen is you've got an object that you're placing it blah, blah, blah centimeters in front of a diverging lens that has a focal length with a magnitude of blah, 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 right? And it says the image form is larger than you want it to be. You want to figure out where to put the object in front of that same lens to produce an image that is reduced by a factor of blah, blah, blah. In other words, you want the magnification of your object to be smaller by that amount. So the trick is start off with your diagram, right? Because what's happening is they've given us a situation, and then we have to come up with a new situation that answers what the question wants us to answer. So we know that the thin lens equation is my friend. And in the original problem, it says I have a diverging lens. That's important. And they give me the magnitude of my focal length. And it's some number. Let's say, for the sake of argument, that it's like 10. However, it's a diverging lens. So it's not 10 centimeters. It's negative 10 centimeters, right? F is going to be a negative number. Right? So it tells you that originally your object is some distance O, and I don't know what O is. Let's say O is 5. right?
Yeah.
Actually, I think O is generally bigger than F, so let's have O be 20 instead of that. Because I think when I pick the numbers, this number is always larger than that number, and that's going to matter. So what's going to happen is when you do this, you're going to form an image someplace. Where is that image going to be? Well, what I can do is I'm going to go ahead and solve for my image position, but I know that my F is going to be negative, so I'm just going to put negative whatever the number I'm given in. O is going to be positive. So when I solve for I, I'm going to have negative 1 over F minus 1 over O equals 1 over I. And again, why is that minus sign there? Because I'm just tacking that minus sign into my equation. Does that make sense?
Okay, so it'll be negative 1 over 10 instead of putting negative 1 over negative 10, right?
Correct. Yeah. You can do positive 1 over negative 10, but that's the same thing as negative 1 over positive 10.
Right.
There's only one minus sign. And I'm just calling out that I'm going to go ahead and just put that minus sign in here so that when I read my question and it says it's got a focal length of blah, 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 I'll just put in 10 for F,
Okay.
right? And put in 20 for O. Now, when I solve for I got to get I by itself, so I'd have, this would be negative O minus F over OF equals 1 over I. You guys see what I did there?
Are you just doing this? Are you just doing this just in case, like, you're not familiar with the calculator, or?
I'm doing this because I hate numbers.
Okay.
I'm trying to do this as generically as possible. Plus, if I do this as generically as possible, it'll be easier for me to tell if there's a bug.
Okay.
All right? Because when I write the equation, when I put the equations in for the key, this is how I have to write them. Because your numbers are all different. So I do it in generic form, and so I like to solve them in generic form to see if I have a bug.
Okay.
So I'm going to do this minus sign, and I got to take I and solve for it. So I'm going to flip both sides. So my image distance is going to be O times F over, well, this is going to be negative O minus F. I could also write that as negative OF over O plus F. That's the same thing. So, blah, blah, blah. That tells me what my image is going to look like. Notice, I'm plugging in positive numbers for O and F, but I got a negative sign up top. So I'm going to have a negative numerator no matter what. And adding two things is never going to be negative. I'm going to get, no matter what, I'm going to get a negative image position. That tells me that no matter what, I'm going to get a virtual image from this lens.
A question.
Yeah.
So every time we have a diverging lens, the formula of the lens, the first formula, is gonna be negative 1 over F. So it's gonna be negative 1 over negative 10.
No. That's I'm trying not to double count my negatives.
Okay, all right.
So what I'm doing is I'm taking that minus sign right here, and I know it's going to be negative.
Right.
And I don't want to run into the issue of negative something, so I'm just going to put that minus sign right up in the front.
Okay.
So when I plug in my number, I'm going to plug in positive 10 here because I know that I've already taken into account that minus sign.
Okay.
Does that make sense?
Mm-hmm.
So that's all I'm doing. So now there's my image distance. And for this example problem, what would I have? Well, that's going to be negative 10 times 20, that's 200, divided by 10 plus 20, so 200 over 30, whatever the heck that is. So 6.66. So far, so good?
Yes.
Now, the fact that it's negative means it's a virtual image, so it's not going to be over here. The image is actually going to show up over here. Right? It'll be 6 centimeters on the left side of the lens, not on the right side of the lens. So far, so good?
Yeah.
Yes.
Now, the problem is, apparently, this 6 times magnification is too big. I want my image to be smaller than that by a factor of X, I think. What's it say here? Yeah, X. So X is some number that they're giving me, and it's different for everybody, right?
Right.
Now, how much magnification do I get here? Let's figure it out. My original magnification was negative I divided by O. Notice it's going to be a negative times a negative, so it's positive. I'm going to have a positive magnification. And it's going to be 6.67 divided by 30. So when I take 6.67 divided by, not 30, 20.
20.
Yeah. So when I take that and divide that by 20, that tells me that my object was magnified by about 1/3 size. But this is too much magnification, right? I need my new magnification. I'm going to call this capital M for new magnification. Has to equal my old magnification divided by X. Does that make sense?
Mm-hmm.
So if X was 2, I just cut my old magnification in half and I divide by 2. And this has got to be my new magnification. And what I'm going to do is I'm going to put my object a different place such that I get the required amount of magnification.
Excuse me, Dr. Fenley, to cut you off. So when you did the M equals negative I over, is that V or?
It's negative I over O. That's the magnification formula for the thin lens.
Oh, okay. And so you have 6.67 over 20, or is that 30?
It was 30 because I was stupid. It's 20.
Okay. But so what happened to the negative sign? It's not there no more?
It's a negative I, but I is already negative, so it's a negative and negative.
Oh, so it cancels out.
Correct. So does that make sense?
Yes.
So now what's going to happen is I'm going to put my guy in a different location. I no longer know where that is, so O is what I'm solving for. But I need my new magnification to be positive, but equal to my old magnification over X. So now what's going to happen is I'll go back and solve with my thin lens equation. And again, I'm going to be lazy, and I'm just going to pull the minus sign for my focal length and just stick it out here. And what's going to end up happening is I'm going to have 2 equations and 2 unknowns. That's my first equation. And I also know that my new magnification, capital M, has to equal negative my new I over my old O, which in turn has to equal my old magnification divided by X. Does that make sense?
Mm-hmm.
And again, I have a number for this and a number for this. So what I can do is when I go to solve this, this is given. That's given in the problem. This I don't know. And I don't know this anymore either, because when I move where the dude is, I'm going to get a different image distance. However, if I take this expression and I solve it, I find that negative I has to equal M divided by X times O. Does that make sense?
Mm-hmm.
So what I can do is I have negative 1 over F equals 1 over O, and then I'm going to replace this with negative 1 over M O over X. That's negative 1 over F plus, or equals, excuse me, equals 1 over O minus X over MO. So far, so good?
Mm-hmm.
Now, again, X is given in the problem. M is figured out in the previous problem. And F is given in the problem. So all I got to do is solve for O. One way I could do that is, here's O appearing in the denominator. That sucks. Let's multiply everything by O. So I'm going to have negative O over F equals, this is going to turn into just like a regular 1. This is going to turn into minus x over my old magnification. And then I'm going to multiply both sides by negative f to get O by itself. So O should equal negative f times 1 minus x over m. And because I don't like this minus sign, I'm going to factor that through. So f times x over m minus 1. So let's see if that's a bug, because I literally don't know, because I haven't thought about this problem since I wrote it.
So for your M, would you plug in for our new M or our old M?
This is my old m.
That's the old M.
Yeah, that's the m I got from the first time out. So let's see if I did that.
Yeah, the mistake was about the sign, because the first one you gave us was 1 minus x over m.
Well, yeah, because last time I was plugging in a negative number for f. I never plug a negative number in for f, but I might have, the other time, I might have left that as positive up here.
Oh, okay, okay.
So it depends on they should both work.
All right.
So what was the old M?
So in this case, we use a positive number for f.
Yeah.
Okay.
I'm gonna let you check for the bug before I put anything in.
Yeah, I'm looking. All right, so of course I go at it differently there, because what I did originally is, let's see here. Let's go back to here's my previous sheet. So what I've got here is I didn't solve for I instead solve for M1. So if I do it that way, M1 would be negative I over O, but I is, so it's negative, so OF over O plus F all over O, which translates to F over O plus F. Just like I might have a sign error here, guys. I'm trying to convince myself this is not equivalent. Because what I have in my key is F over F minus O, but it looks like I should be F plus O. Yeah, I'll have to go back and fix that, guys, I think. So don't put anything in yet. But you see how to approach it, right?
Yes.
Yeah. Yeah, the tricky thing is, you know, to, when you're doing it, what did I just do? Is watch your signs, because you can see it's super easy to screw your signs up.
I had a question about 26.4.
Okay, well, let's take a look at it.
I tried to do it, and I thought it was like a straightforward question, you know, just the whatever. And I did it like 6 times, and I got it wrong.
All right, well, that's usually when you go away and ask to see if there's something going on. 26.4, you said?
Yeah.
Okay, this one should be pretty straightforward, because it's literally the ratio of your two focal lengths. So here's the thing that I might ask you is, did you notice the units on those two focal lengths?
Yeah, one's in meters and one's in centimeters, and I converted it to meters, both of them, and then I still got it wrong.
All right, did you have the right one on the top?
It's a sign.
It should be F.
Probably the minus sign.
It should be the first one over the second one,
Yeah, that's what I had.
and there is a minus sign. Yeah,
Okay.
yeah, because it's negative FO over FE.
Okay.
So that's the formula. You will get a negative answer.
Okay. I kept getting positive answers. That's why.
That's why. Yeah. What's going to happen is for that kind of telescope, you're always going to end up with your picture inverted. And if you're looking at like Jupiter or something, big deal. Jupiter's upside down. It looks fine to me, right? It would be less worthwhile to have that same telescope be used for a terrestrial purpose, because if I'm looking at like a building in the distance or a mountain in the distance, I don't want the image of the mountain to be inverted. So I would probably want to have a third lens to invert my image, even if it doesn't contribute much to my overall magnification.
Okay.
But for a lot of your two-lens telescopes, you'll end up with inverted images.
Okay. Thank you.
I also had a question about 23.7. I keep.
Okay, that's the one with that's the touchy one, right?
Oh wait, never mind. We just talking about that.
Yeah, we were just talking about that. Yeah, and again, that one it's not bugged, but if you aren't super ridiculously careful, you're gonna screw yourself up. So I would avoid rounding when you don't have to, but when you're using the pi function, do 3.14 rather than 3.1415926 or whatever, because inside that sign function, even that tiny little difference can make a huge impact on your final answer. It's not going to be a linear sort of thing. So that's probably what's screwing you up for that problem.
Okay, I'm trying it right now.
Okay. Anything else you guys are particularly stuck on?
Yeah, Dr. Fleming, is there any way you could take that one off then, being that it's so super sensitive?
Just
really.
I'm just telling you, it's really sensitive to that one thing. The stuff inside the sign function is the part that it's super sensitive to.
You always try. Okay. I guess I'll just ask you in office hours because I don't think it's a different chapter.
You can just put 3.14, right? You don't
want right, yeah. The value of pi that I used in the key was 3.14. I should have used the pi function where it will keep it to an arbitrary number of decimal places, but I was thinking, I only want my answer to 3 sig figs, so why go beyond 3 sig figs? And the answer is because inside the sign function, it makes a huge difference. But because I was being stupid, that's the error that I made, and I don't want to change that. So I'm just telling you up front, do it that way, you'll get the right answer.
Okay, so we could go back in now and try it again.
Yeah.
Okay.
I haven't made any changes to that one at all. It's just super sensitive because of the periodicity of that function.
So do we wait to do 25.4 until you fix it?
If you give me come back tomorrow.
I'm not touching it until you fix it.
The basic process, and in fact, what you probably want to do is if you've opened it, you'll want to submit an answer. You're going to get it wrong, probably. After I fixed it, you'll open up a new one. Because what's going to happen is if I make a change to a problem that's already out there, if you've opened up the broken version of the problem, it's going to keep giving you the broken version of the problem until you answer.
Okay, so just open it, get it wrong right now, then wait.
Yeah. When you open up the new one after it's been fixed, you'll get the fixed version. You'll get it right. So.
Dr. Fleming, I have a question.
Yes, ma'am.
What's the difference between the power of refraction and the power of lens? The same thing?
Well, no, there are different ways of referring to the same thing. When we talk about the refractive power, P, that's just 1 over F.
Right.
That's it. And it's useful because if you think about the thin lens equation, right, you got that 1 over F that keeps showing up again and again and again.
Mm-hmm.
And what's going to happen is if you talk about the terms, if you talk in terms of like actual distances, you'll have like 1 over 0.2 is going to be like 5, right?
Mm-hmm.
1 over 0.3 is going to be like, I don't know, 9. Well, it's easier to take 5 minus 9 and just say, the answer is -4, than it is to say, 5 minus 9, then take the reciprocal and get some super tiny decimal.
Mm-hmm.
So that's why when you look at like your prescriptions for like reading glasses or something,
mm-hmm.
they end up being like nice, happy round numbers. Like I have a reading glass prescription of 0.5 or -0.5. All that is a focal length in diopters rather than in inverse meters.
Okay. Because on those assignments, when I was doing it, when they asked about the power of refraction, I just calculated normally, like 1 over I plus 1 over O, and I put the number in and it was right. But when it asked about the power of length, it wanted me to revert 1 over F, convert it into meter, then divide it again, 1 over that number, and put in the
I'm not sure the wording. I don't recognize where I had that particular wording. Can you tell me which problem you're referring to?
So when I did 26.1, I didn't have any problems.
Uh-huh.
But when I did 26.2, I had to convert F in meter.
All right, let's look at, because it sounds like what you're describing is a very subtle difference in wording, and I don't recall the exact wording for that problem. So let's look at that real quick. Yeah, so in 23.1, you're looking for the refractive power, which is P, 1 over F.
Right. Mm-hmm.
And in 26.2,
they said the power of length.
no, they should be the same thing. Your answer should be in diopters for both of them. Now, what is true is that diopters are 1 over meters, and in question 2, all of your distances were in centimeters.
Oh, okay.
And in question 1, some of many of your distances were in meters.
Okay.
So that might have been the issue that you had, was just that a diopter is specifically 1 over meters, not 1 over centimeters.
Okay. Okay.
I got it wrong still. Using the 3.4.
Yeah, I got 23.7 wrong again.
Because first we find the X, XL, and then we find XC, and then we find Z, and then we plug into.
So after you find Z, then you find your maximum current by taking your voltage divided by Z.
By Z, yes.
Then you're going to have that maximum current times the sine of omega t minus pi over 2.
Yes, and I still got it wrong.
Did somebody get it right already? We use radians for those, right?
Must be in radians mode.
Right.
So the whole thing have to be in radians, or just
when you do the sine function, you got to be in radians mode. It doesn't matter anywhere else except where you do sines.
Well, yeah. See, that's what I'm saying. I did sine.
Hang on. So
Check me out.
I'm pulling up Allah's specific last answer.
Yeah, put mine to two, please.
Yeah. Yeah, Allah, I don't know what to tell you other than be careful. Something in there is not right.
So what I put in is not right.
Something I can't tell you without seeing your work more specifically what that is.
You
But
want me to email you my work?
that'd be super awesome.
Great. That's what I was gonna do this morning. But
Yeah. Sorry, I've just been this Canvas thing is giving me a complete meltdown for these exams, and I'm already freaking out for the final next week. So I've not taken any office hour appointments all day, and that's never a thing that I do. I usually don't turn students away, but talk to me tomorrow. I will be available tomorrow, but I need to get this thing finished because I've got 3 exams, and none of the exams are working right. So.
Was chapter 27 the last one?
I'm sorry?
Was chapter 27 the last chapter?
Right. The last chapter we're going to do is chapter 27. And we're not even going to do all of chapter 27. I'm hitting on a couple of these things because they do have instrumentation issues. Like being able to do thin lens interference can help you in some chemistry experiments. Being able to deal with diffraction and diffraction peaks can help you in some chemistry experiments. Think about like Rosalind Franklin when she discovered DNA and the structure of DNA. Do you know how she did it? Yeah, of course.
No.
She did it with X-ray diffraction, right? What she did is she diffracted X-rays through the lattice of a DNA helix, and was able to infer the structure of DNA based on that. And of course, she publishes, or she sends that research to Watson and Crick, and they get all the credit for it, and they win Nobel Prizes, and she gets screwed because she's a woman. But whatever.
Right, exactly. That's why I was like a woman.
Yeah.
It was two men, because when I read, I knew it was
ripped off the word from the woman. She was the one who
Okay.
did physics
Okay.
to figure out what that is, and she was doing diffraction experiments.
All
So
right.
I wanted to hit those sections of chapter 27 because those are the sections of chapter 27 that you guys, as mostly biologists and some chemists, are going to care about the most.
Okay.
So the chapter after that is special relativity, which is dear to my heart, but you will care about not at all. So we're not going to talk about that. It makes me sad. All right.
Dr. Fleming, if you found out that it was bugged, are you just gonna give us like, and we got it right, like the instant we typed in the are you just gonna give us the
If there's a bug, what I'll do is I'll fix it. But I haven't had any other, with the exception of 26.4, which I think is bugged. I haven't convinced myself that it's not just me writing in a different form because I solved it a different method. And they may be equivalent, but I'm not sure enough that I'm confident. I'm just going to redo the key. But I'll fix that, at the latest tomorrow. Just do it. It's not that hard. But the rest of them should be okay. You have something else you're suspicious about? I know that 23.7 is super, super touchy. Again, it's very straightforward. Calculate XF,
25.4.
calculate Z, calculate Imax. Do Imax times the sine of omega t minus pi over 2.
So what about 25.4?
That was the only one we were talking about. I said I will fix that.
Oh, okay.
Yeah.
Okay.
Yeah. But it could be another one of those. It may just be that it's also super touchy because, again, anytime you have those weird reciprocals, if your denominator is a little bit different, it makes your number very different. So it could be a round-off thing there, but I'm not sure.
Okay.
But it's more than likely a sign error because signs are an absolute pain, especially when I'm trying to do the key. And I'm giving the numbers in one sign, but I'm calculating with a different sign. And sometimes that's challenging. So I might have screwed that up.
Okay.
So I need to sit down and think through that and just try again.
Take your time.
All right. Any other questions about this exam? Do you guys feel like you know what you're doing?
So 6 o'clock?
That's what I'm aiming for, but don't count on it. It's probably going to be late. But either way, it's not going to be due till midnight on Wednesday, right? If it's midnight and it's still not up, I'll give you an extra day. But
Can you please not make it too hard, Dr. Fleming? Because
I'm trying not to make it hard, but I am trying to make it so that you can't make your way into the answer. And this is one of the things, like I have to write all new questions because, I've poked around on Yahoo Answers and Chegg, and I found a whole bunch of my old exams, like right up there. And normally it doesn't bother me so much because if you're studying off stuff like that, it's not going to help you in the middle of an exam or you have to do it on demand. But now I got to worry about you guys Googling stuff. And so I'm trying to avoid making it a situation that you can cheat your way out of without knowing some stuff.
But didn't you say you like making it personalized, so like it's not something that you can Google? So I don't think that's a change.
Well, yeah, but you can there's plenty of sites where you can go in and say, hey, what's the answer to this, and get an answer within a couple hours. So
Hours. We have 2 hours to take a test.
well, that's the other reason why there's a time limit. If you're going to Google your way through my exam, I'm going to make sure that you don't have a whole lot of time to do it. So, but yeah, that's just, I'm trying to play the hand we've been dealt. And I want it to be, demonstrative of what you know. I don't want it to be unfair. But at the same time, I have to be aware that it has to be a reflection of what you know and not what you can look up.
Right. I have a question outside of the exam. So, are we done with labs?
We're not going to do a lab this week.
Oh, yay. Okay.
So after the go
I generally try to avoid doing a lab the last week. So yeah, we're not going to do a lab this week.
Sorry.
So after this week, it's really just final time?
That's it. We got 2 more class days worth of stuff. We'll probably spend some of that doing some review stuff. And then, yeah, we're out, guys. This is it. I should,
A little bit longer, maybe 30 minutes, and I'll take you off. Okay? I'm sorry, Dr. Fleming. I'm currently in the hospital. I'm sorry.
Okay, that's cool. Have you had a kid yet? You said you were like.
No, I'm finally dilating. So.
Oh, good job. You okay?
Oh yeah, physics baby.
Physics baby. I still just want to come to class.
Okay, final baby.
Final baby.
All right, hang in there. I'm got my fingers crossed for you.
Okay.
We done with the guys?
Yeah, I'm done, guys. If you don't have any more questions, go away. I got stuff to do.
Dr. Fleming, is there gonna be any way we can get some extra credit?
Well, remember, I build extra credit into the homework, right? I'm putting in this much homework and requiring this much homework. So,
You know, 90% is almost all the homework.
I'm saying if you did 90% of the homework, that's 100, right? You've gotten, well, 7%. It's 93% is the number I'm using. But if you're doing 93% of the homework, you've got 100. If you did all the homework, that's 107 and something, right? So there's homework stuck in there.
That's a lot of
Are you
homework.
gonna grade labs before?
God help me, I'm trying. All right, I'm working on it. It takes a
on final time, so we know kind of where
I got a lot of things to do. I'm working on it. So.
Now you know how we feel, Dr. Fleming. We have all these
You know,
classes.
you know.
Like, that's.
I'm just ready to be done. That's fine.
I feel you guys. I appreciate that you guys are showing up every day. You know, in these weird circumstances. You know, I want you guys to pass this freaking class. I do. You know,
Hey, Dr. Flynn, one question. Yeah.
I'm not. I don't give guineas, but I do try to look out for you.
All right.
I'll work with you. Don't
Yeah.
worry. We're gonna do up.
What's your question? You said something?
Yeah. So you were mentioning that we have this big homework, but then you actually had your hand like half of it. You know. So does that mean we only have to like do half of it because your numbers are like if we do 90?
The number of the syllabus is 93%, right? So if I put out 1,000 points worth of homework, I'm only requiring you get 930 of those points. That extra 70 points, that's gravy. That's extra credit built in.
Yes, I mean all of it.
Yeah.
Mm-hmm.
It also means that if Canvas says your homework average is a 70, it's really 93%. Or if you take that divided by 0.93, your actual homework average that I use to compute your final grade is higher by 0.93. So.
Okay, and the final exam rules still apply. So, like, if I get an 80 on the final, hypothetically speaking, I get an 80 on the final exam, and all my other grades are lower, that replaces it, right?
Yeah, let's have that conversation. I have a file just for this exact question. Hang on a sec. Give me 2 seconds.
Now you can show it to the whole class.
All right. All right, don't share that. Don't share that. All right. Good news is I think it was not your final or not your exam that showed up there. It was somebody else's exam. All right, where is that thing? Grade check. Here we go. So this is the method that I use for calculating your final grades. All right. So what's going to happen is you've got a bunch of categories: homework, labs, exams, yada yada yada. So what's going to happen? And you can do this at home, kids. Try it yourselves. So your course grade comes from your homework is 20%, your labs are 20%, your exams are 25%, your quizzes are 15%, and your final exam is 20%. Now, what's going to happen is the final exam rule says that if the final exam score is higher than your exam average, I throw your exam average out and replace it with the final exam score. So the final exam can count extra if you do well on it. So let's imagine you come in and you got 90% of the homework done, right? And let's say your labs are, not great, but it's sitting right there. And let's say your exams are terrible, 50, right? And let's say your quiz averages, I don't know, they're 75. Remember, I dropped 4 of them, which helps a lot, right? And let's say you come in on the final, and obviously if you were this person and you didn't show up for the final exam, then what's going to happen is you'd get a 56 and you'd fail. So definitely take the final. Now, if you came in and you were this person and you got the same grade on the final that you got on the regular exams, yeah, that only took your grade up to a mid-level D. Not the best. So this person isn't quite getting where they need to go. However, let's say that this person comes in and they do an 80 on the final exam. Now, what's going to happen is, if this is an 80, I have this set up with an if-then statement where it's ignoring that 50. Notice, if I make that 50 be 0, no change, because as long as this number is smaller than that number, it doesn't even look at that number. It uses that number twice. So, person who got an 80 on the final exam is going to walk out of here with a B. Right? Does that make sense? If that same person only got, say, a 70 on the final exam, however, that drops them back about 5 points. If they get a D on that final exam, they're barely passing. So that kind of gives you a sense of where to do that. And again, all I'm doing to get this number is I'm taking 0.2 times the homework score, plus 0.2 times the lab score, plus 0.25 times either the lab or the final exam, depending on which is higher, 0.15 times this, and then 0.2 times this. And I'm adding them all together. That's your final grade. So you can do this at home.
Can you email this to us?
Why not? Can't spell today.
Oh yeah, you're the best, Dr. Fleming. All right.
Yep. Where did I put that? Desktop. Grade check. Doom. There we go. All right, there it is. Any other questions?
I'll see you later.
No, you're good for now.
Nope.
All right, guys. Have a good one. Study hard.
Bye, Dr. Fleming. Have a good day.
Bye, Dr. Flem.
Hi, Dr. Fleming. Don't make our exam too hard. Thank you very much.
Thank you.
Bye. Saying that